So this could be seen as a continue of exercise 65. We have more delicate phenomena. So I'm not going to prove all the exercise, so let me first state it. So you can think this as a theorem. So let R be a domain, similar setting as last exercise, exercise 69, with K is fraction field. And weigh a K vector space. So quickly recall last time we have discussed about take a submodule of K, tensor over R with K vector space is isomorphic to way, right? So now today we talk about firstly for R module M, no restriction. No restriction, it is contained in K or not. There is R linear isomorphism. Way tensor with M over R is isomorphic to way tensor M quotient by torus over R. Where this M torus is the torsion submodule M. Secondly, for any R module M, if it is torsion, this implies that this is 0. Actually, this comes directly from the first one. So the main part is the following. If M is not torsion, and if V is not 0, so recall V is vector space, then this is non-zero. So whenever you want to check tensor product is non-zero, requires some work. Lastly, if M is an R module and N is a submodule, such that M quotient by N is a torsion R module, then we have V tensor is N is the same as V tensor is M. In some sense, if they only different by torsion, then that doesn't hurt the tensor product. So this is a really weak way how to really prove it. And moreover, this map is just naturally like this. So let's add the first one as a corollary of those, which says under the same notation, V tensor M in V tensor M. Sorry to give you a criterion of this. If and only if small v equals 0 or M is in torsion submodule of M. Right, particular, this gives you also another description of M torsion. This M torsion hence become all those kernel from M to mapping M to one tensor. Because exactly by this form, right? It tells you under this R linear map, all those one tensor M equals 0 corresponds to exactly those M in M torsion. Okay, so I'm not going to prove all of it. Let's just prove the first one, the third one. So again, we have to start with bilinear map. From V product M to target. And the map is constructed as follows. This is R bilinear. Checks easily, and so this gives this map of tensor products. Let's call it F. V tensor M is mapped with tensor M bar. Let's construct the inverse of it. Let's start with V product M, map it to V tensor M, right? And then notice that it factors through M quotient by M tor, because if small m is in M tor, by definition, there exists some R such that non-zero, let's say non-zero, otherwise any element is killed. Non-zero such that Rm equals 0, then small v tensor M equals how do we give it a R? So V is K vector space, with K vector space, and so in particular you can have this weight M is a R module or a K module. M is R module. So in particular non-zero R, you can write this, no problem, because V is a K vector space, right? And so you can move this R to the right hand side, and this gives you 0. And so this map, let's call it G vectors, right? This is mapped to V m bar. So m bar is mapped to V tensor m. It doesn't depend on the choice of the lifting of m. Okay, so what is left to check is that just this is inverse to each other. Wait, sorry, not yet. This is just bilinear map, and so this induces universal property of tensor product, this map. So let's call this G, which maps V tensor m bar to V tensor m for whatever lifting of m bar to m. And then check this G compose F is identity on V tensor m, and F compose G is identity on this V tensor m quotient m tau. Then left it to check. Okay, then let's do the third one. If M is R module, N is a submodule, then M quotient N is torsion, and we want to show that okay, we have this isomorphism. So let me copy here. This is our goal, to show that we have this map. Okay, so the solution is start with bilinear map. With this is bilinear, and so it induces a map from V tensor n to V tensor m. So let's call this F. This is not the identity map because they're not the same module, two sides. So we construct inverse. So the difficulty is that, so you cannot simply say that I take Vm and then map it to V tensor m, right? Because m may not in n is a submodule of m, but not the inverse. So this doesn't work. What you do is that you find a way to turn it into n, because for our element here, this is torsion. This is torsion means there exists some R such that it's 0, which means it's falling to n, right? And so how do we map it? Suppose this m, there exists some Rm in R such that Rm times m is inside n. So we map it to V Rm times m, but here we multiply by 1 over Rm. sorry, this is the tensor product. Like this, because this is actually the same as, if you move this R linear, because this is R module tensor, move this RM to the right hand side, this is the same as. But you can, inside with tensor M, this is the same, but in with tensor N, this is not in with tensor N. Okay, so let's first check this, let's call this G tilde is well defined, which means doesn't depend on the choice of RM, right? Suppose there is this RM, RM prime, such that both works. Then what do we have? We want to check that it gives you the same. Right, this is what we have to check. So let's check it. So this is the same as RM prime, RM prime, RMM, and then let me just move one RM prime to the right hand side. This works because this is a K vector space, so what you left is still in K, is okay. At the same time, I could move this to the right hand side, because M is R module, this is still in R. But then this cancel, this gives you RM prime with RM prime M, and so this is true. Okay, so after we check this means that of course both time we are talking about non-zero RM prime. So then what do we check? We going to define this map and then check its R bilinear. And then this implies that we have a map G from with tensor M over R to with tensor M, with tensor N over R, it's G tensor M, map it to whatever R, whatever R that works. And then again one checks this identity inverse to each other. And then we are done. So